Hey programmers, Alvin from CoderByte here. Welcome back to another video in our series on linked lists. And this time around, I want to walk you through how you can reverse the order of nodes in a linked list. So that means our learning objective for today is to implement both an iterative and a recursive solution to reversing a linked list in place. So let's start by formalizing this problem. So what I want to do is write a function called reverse list that takes in the head of a linked list as an argument. My function should reverse the order of the nodes in the linked list in place. So that means I don't need to create a new linked list, and I shouldn't create a new linked list. I want to modify the existing node. So that means I can reassign their next pointers. If I look at this last constraint over here, it says that our function should return the new head of the linked list, right? When we reverse the order of nodes in a linked list, that means that the head becomes the tail, and then the old tail becomes the new head. So before we just try to code up a solution for this problem, let's actually whiteboard a few ideas. So let's say that this is the input into my function, right? So I'm going to be given the head node or the A node in this linked list. Looks like this particular example has values A, B, C, D. I know when it comes to reversing the order of nodes in a linked list, I just need to make sure I can invert all of these next pointers, right? So for example, if I see this arrow pointing from A to B, that means A's next is B. But by the end of this linked list, those two things should have flipped in their order. So it's really the case that B's next should become A. So how can I accomplish that logic within my code? So let's start with some familiar concepts. So whenever you're tackling a linked list problem, I think you should start with the basic strategy of having a current pointer variable that you can use to traverse through the entire linked list, right? So obviously I'm going to begin this current pointer pointing to the head of my linked list, which is A. So I'll use kind of the letter C over here to denote that my current node that I'm looking at is A. So along with this current node, I think in this problem, I'm also going to need access to another node. I'm going to need access to the previous node, right? We've seen this strategy in the last episode, and I can basically reuse it over here. So whenever I start my linked list iterations, I'm actually also going to initialize a previous pointer, which at the very beginning kind of means that I guess previous should start at null, right? So I'm going to kind of leave it in this open space over here because there's nothing that is previous to A, right? Because A is the head node. There's never anything that comes before the head. Cool. So let's say I'm beginning my algorithm over here. So my current node is A, and my previous is basically set to null. So a few things I'll need to do is I need to make sure that I can reverse the kind of direction of all of these edges, right? All of these next pointers, right? So right now, A is the current head, right? I know by the end of my algorithm, it should become the tail, right? It should point to nothing. So there are a few things I should do over here. Now that A is my current node, I can set currents next to point to the previous. So in other words, I'm going to take this edge out, I'm going to kill it. I'm going to set A's next or currents next to be the previous. Since previous is null right now, that would kind of give it this edge over here pointing to null, right? Which is good to go. And now at this point, I can shift my pointers for previous and current over by one frame. So now that my previous pointer is at A and my current pointer is at B, I can perform the same logic, right? I'm going to reroute my currents next to be my previous node. So I'm going to take this out, take this pointer out, and then reroute the next over here. You can already see how this flows, right? I'm going to continue this pattern, which means I can move my previous to B and my current to C. Notice by the end of the algorithm, when I set D's next to point to C, it looks like D actually no longer is the tail, right? It's technically the head over here. So this code looks pretty good to go. Although things are still ordered left to right, the connections in this diagram are totally correct, right? D is now the head because it has nothing that points to it, and A is now the tail because it points to null over here. All right, so here I am in my code editor, and I just have some initial code that we can work with. So of course, we're going to need to have a linked list to deal with. So here's a classic node class, and we just manually create some instances of nodes and then link them together through some straightforward assignments, right? So it looks like when we create these connections, the order of nodes in our original linked list is just A, B, C, D, just like our example. I also went ahead and created a quick little print function that will just print out all the values in our linked list in order. That way we can visualize our test cases. So here's what we'll do. Now let's start by just printing out the original linked list. So I should just see A, B, C, D. Cool, and there I see my original linked list. We of course want to implement a reversed list function as well though. All right, so let's begin defining our reverse list function. One thing to keep in mind as we create this function is our function should return the new head of the linked list, right? They asked for that specifically in the prompt. And that makes sense because if you reverse the order of nodes in the linked list, then the tail becomes the head and vice versa, right? So I'll just keep that in mind. As I start to code this one up, I'm going to choose to solve it initially with some iterative code, right? So let's start to lay down our foundation. So in our drawing, we described how we needed 2 pointers, right? I needed a previous pointer, and I also need my current pointer, right? The current pointer is very easy to set up. We always set it to initially be the head of the linked list. Now when it comes to our previous pointer, if you recall how I started the diagram previously, since our current is head and there's really nothing previous to the head, you can kind of just initialize this previous pointer to be null. Now we'll lay down some classic linked list pattern code where we have a while loop that iterates while current is not null. All right, so basically while I'm not at the end of the list, I need to keep going. Cool. So this code's looking pretty good. Let's also lay down that classic pattern of just traversing through the linked list. So I can iterate by saying cur equals cur dot next. So this should just move through my linked list in order. But now I need to think about how I should be reversing the order of nodes in my linked list, right? So I'm going to need to write some logic within this while loop. Let's think about the first iteration. So obviously on the first iteration of our linked list traversal, cur is going to be pointing at A, and previous is going to be pointing at null. And that actually works out pretty nicely because by the end of my function, A's next should be null. So I think an important pattern to write here is just invert the direction of A's pointer. I can say, hey, my current's next should become, or point to rather, the previous value. So on the first iteration, that means that A's next pointer will now point to nothing, kind of like it does over here, right? Cool. But at this point, I need to make sure that I don't break any of my previous code. So if you look at line 32, this is reassigning cur.next to point to the previous. That means over here, I'm setting current also equal to the previous. So that wouldn't work out too nicely. So this is what I mentioned when we sketched out our diagram. You're probably going to need a temporary variable to make sure you have access to the rest of the linked list. So what I would do is something like this. Maybe I'll just say const, and I'll create a variable to kind of hold the next. So I'll save it here before I reassign it, right? So that means on line 36, I set cur equal to the next, just like this. All right, so that pattern's pretty straightforward. I think at this point, we also need to reassign and shift our pointer for previous, right? So it looks like over here, we set current to be the next. That's very classic linked list code. Let me also say previous should now point to the current, right? So I'm just shifting my frame of reference over by 1. So for example, let's say we're at some iteration. I'll use P to represent previous and C to represent my current. Let's say my previous is A and my current is B. When I perform this operation over here, I'm just moving those pointers, right? So P goes over here and current points over here, right? I just shifted my frame of reference over by 1 using that sliding window strategy. Cool, so that's looking pretty good. And I think that would actually accomplish the reversing logic. Something I have to also implement in my code is I need to return the new head of the linked list. Recall that the new head would basically be the old tail of the linked list, right? So after my while loop's done running, if current is equal to null, that basically means that we're kind of at the end of our linked list. If our current's equal to null, then I'm basically like past the D over here, right? I'm a little past the last node. And so that means previous would be pointing to the last node D. So I can just actually, after the while loop, I think just return previous. It should be pointing to exactly what I need. So let's save this code. Again, I'm returning previous over here because that would technically be the last node of the linked list, of the old linked list, which is now the head. Let's test this code, right? So I'm going to print out my linked list before I reverse it. And I'll also print it after I reverse it. Right here, I'm calling reverse list and it's returning me the new head. I'll also put some dashes here. Now we can just separate our output. So let's see what we get. I should get DCBA. Give that a go. And there we have it, DCBA. So this code is looking pretty good. It wasn't too difficult, but let's be thorough in our testing, right? What I would do now is maybe test our reverse list function on some lists of varying size, right? So I tried 4 nodes. Let me see if 3 nodes works. So what I can do to fix that is I can just not add D to my list. So this just means A's next is B, B's next is C. So when I run this, am I able to reverse 3 nodes? Yep, ABC turns into CBA. Can I do just 2 nodes? So AB should turn into BA. Nice. And let me try the single node example, right? So if I had A, it should still just return A, I think, right? Awesome. So to wrap up this iterative solution, let's discuss the time and space complexity of this. So the time complexity would mostly come from this while loop over here. As we can see, it just iterates through the entire linked list in the worst case, right? So I'm going to say it's O of n time, where n is the number of nodes in the list, of course. And when it comes to the space complexity of this one, I do believe that it's constant space, right? I only create a fixed number of variables. I don't create any arrays over here either. So I have O of n time, O of 1 space, which looks like a pretty fast and efficient solution. But just to be complete in our understanding, why don't we also solve this through some recursion? And I think the recursive solution is actually easier to express in some code. So I'll start to write my reverse list over here. And before I forget, I'm going to create my linked list with 4 nodes, right? So this means right now that my linked list has A, B, C, D. And for this recursive implementation, it's really going to be the same strategy again. I'm just kind of viewing it through the lens of recursion. And so I'll have to figure out how I should pass my arguments over here. So here's what I'll do. I'm still going to take in the head of my linked list over here. And I can also take in some additional arguments I think would be useful. I think for this time around, why don't I add like an optional argument? So in JavaScript and in many programming languages, if you wanted like an optional argument, you can say things like a variable name like previous, and you can assign it in line in the function signature. So previous, I'm going to initialize that to null. So if I write code like this in JavaScript, this is true even for languages like Ruby and Python, that means that if someone does not pass in a second argument called previous, I'll just assign it to be null. So let's say I console.log these 2 values. So I'll console.log head and also previous. So that would technically be running over here, right, on this reverse list. Let's give that a shot. Like you see in my terminal, head is pointing to the head node that I passed in, which is the A node, and previous is actually null, right? So this is just me using some like default arguments in JavaScript. So I can use that pattern over here if I like, or you can separate it into like a main function and a helper function. It's really up to you. For brevity, I'll use this pattern. And now that I have my 2 pointers, right, for head and previous, maybe I'll rewrite this as maybe current. So let's start to describe what this recursive function should do. So I know it should have the effect of at least traveling through the entire linked list. So recursively, that pattern is very straightforward. We covered it many times. I can call my function again, and my current should now be shifted to current next. And for the sake of maintaining my previous, I'll pass in the current as the next previous, right? I'm just shifting my frame of reference. So now I want to consider some base cases, right? So the straightforward base case I should probably always consider when I'm dealing with linked lists is if I'm at the end of the linked list, or basically if my linked list is empty. So why don't we check that? So if we're at the end of our linked list, that means if our current pointer is equal to null, that means we're basically done over here. So we need to be sure to return. But the question is, in this problem, what should we return? If you remember the prompt, they want us to return the new head of the linked list, right? If my current is equal to null, that means my previous would be technically the very, very last node of the linked list, which is now, I guess, the new head. So if current is null, then I can just return previous. So that'd be returning the new head. So that's a nice base case. And then with that, I actually need to perform the rerouting of those next pointers. So I'm going to try to translate this pattern over here, which I think is pretty straightforward. I may need a temporary variable though again. So I'm going to set current next to point to the previous. So that would change the direction of its arrow, just like I did in the iterative version. But if I do that, then I would lose access to the actual next over here to kind of go through the rest of my linked list. So maybe I'll kind of save that into a temp variable. I'll say my next will be cur.next. That way, when I reassign it, I can still recursively call on the rest of the linked list over here. So it's very analogous to the patterns we wrote over here. So this code is looking pretty sharp. What I want to be sure I also do is make sure I pass up the new head of the linked list all the way to the tippy top. So my base case returns some value. I need to make sure that I pass that return value all the way up the call stack. Cool, right? So when I call reverse list on the A node, I should be getting the new head. I should be getting the D node basically, right? So let's test this code. Make sure I have all my test cases in. Yeah, so my initial linked list should be printed as ABCD. Then when I reverse it, I should get DCBA. So let's give this a gander. So ABCD, DCBA, awesome, and there we have it. So we can see that our recursive reverse function totally works, but let's kind of trace through what really happens under the hood. I do find that many students kind of have less intuition and instinct for understanding how recursive code works, but I'll show you that you can really understand it really in the same way that you're comfortable with an iterative solution, right? So let's really trace through things over here. So as I trace through this, I'm going to represent my current pointer or my current variable with C, and I'll represent previous with a P over here. So because we're making a top level call to our reverse list function, no one's going to pass in some previous argument, which means that we're going to assign it to null by default. So to represent that, I'm just going to put my previous pointer kind of in this open space over here, where there's nothing over here, so I guess that technically means that it points to null, right? So it looks like when A is the current, that means its previous is null. And we're gonna have many stack frames like this, but let's start tracing through it. So in this first top level stack frame, current would be checked, right? Is current equal to null? That is A equal to null? That's not the case, so I can continue to the rest of my code, right? I set next equal to current next. So I'm actually going to have, I guess, technically 3 pointers here. Maybe that makes it clear for all of you. So next is going to be over here in this first frame. And then I set current's next to be the previous. So I kind of reroute things like this, right? A's next now points to null. And so we're in good shape. Then if I look at line 54, I make a recursive call, right? And so when I pass in different arguments over here, I'm basically shifting the frame of reference for this P, C, and N, right? Which means previous, current, and next. So let's kind of do that. So I'll kind of denote another call stack frame with a little line over here. So if I look at my recursive call over here, it looks like the current is now going to be what the next was. So it's like this, right? So current and next are aligned, right? This is the previous frame, and then down below is my new frame. And then it looks like the previous argument is now going to be taken as the old cur, right? So it looks like P is over here, right? My new previous argument is the old current over here. And like you expect, as soon as I hop into this frame, I would check, is the B node, right? Because current's pointing to the B node. Is the B node null? It's not, so I can run the rest of my code, which means I set next equal to current's next, right? So next should actually lie over here. And then I do the rerouting, right? My current in this frame is B. I set B's next to be previous. So previous is pointing to A. That means B's next should point over here. And of course, along this way, whenever I reassign any node's next pointer, that means I would kill its old connection, right? So I kind of have these removed. And the same thing happens, right? Now I make another recursive call and I shift my frame of reference in this new stack frame, right? So basically I would end up with this pattern, right? Have P, C, and N. So previous, current, and next on this frame, and I would do that rerouting, right? I check, is current equal to null? It's not, because I have my current set to this C node. And so what I do is I set next equal to the current's next over here, and then I do some rerouting, right? Current's next gets reassigned to the previous, right? Remember, I'm looking at this bottom frame over here. I think this would continue all the way through. So once I finish dealing with the D node, right? So let's say I'm at the stack frame where D is my current node over here. Technically, I would make one more recursive call, right? So I basically would have this scenario at the very end. Previous is pointing to the D node. Notice how it's aligned vertically. And then my current is actually pointing to null, right? Because there's nothing over here. And that would actually be my base case, right? I check if current's equal to null. That's true, so I should return previous. Well, in this stack frame, previous is the D node. That means I would return this D node all the way up the call stack, right? So notice that the base case returns and every recursive case returns. So basically I'd be returning this D node all the way up the stack, which is why my function is able to work. Cool, so hopefully now you're feeling a little more comfortable with understanding how this recursive code works. Again, it really implements the same strategy compared to our iterative code. But to wrap this one up, let's discuss the time and space of this one. So the time is going to be the same. The time is still O of n, now where n is the number of nodes, because I would have to make n recursive calls, right? One call for every node of the linked list. So O of n time. In terms of the space complexity, we're going to say it's O of n space because we have to use the call stack, right? I would have a stack frame for every node in my linked list. So we have O of n space. If I compare these two solutions, if you wanted like the most efficient in terms of time and space, you'd probably prefer the iterative version. However, I do think there's a massive value in understanding how to implement the recursive version. For one, I think it's way easier to implement. So there you have it. In this lesson, we covered how to implement an iterative and recursive reversal for the order of nodes in a linked list.